All right, moving on in question 3, so I have a little scenario here about removing tarnish from sterling silver. So I'd like to do a little diagram just to kind of visualize what's going on. So let's pretend this is my sterling silver, and I'll just label it SS. And on top of this sterling silver, we have some sort of tarnish. So I'll just put that as the tarnish. So this tarnish is represented by silver sulfide. Okay, so this little part that I shaded in, this is silver sulfide. And so the question is, you're going to remove this silver sulfide tarnish, and after removing it, we need to calculate how many moles of silver atoms did we actually remove, which is this part. All right, well, look at our data table. Before removing the tarnish, the mass of this whole thing is 409.21 grams. And then when you take this tarnish off, so if I'm just left with sterling silver, its mass was 398.94 grams. So if I take the difference between these numbers, that will tell me how much tarnish I actually removed. But that'll be in mass. So let's write it down over here. So I'm going to say that the mass of removed is 409.21 grams minus 398.94 grams. So I removed a mass of the silver sulfide as 10.27 grams. Okay, but again, I want this in moles. So I'm going to convert this to mole using, again, I like to use the formula. So we're going to say N equals M over M. Now, the molar mass is given to me in this question of the silver sulfide. So just remember, as I'm doing this, this is not the answer for silver moles. This will give me the moles of the compound silver sulfide, which is 0.04. I'll leave a few decimals, 144. This is moles of Ag2S. So that's not what I want. I want the moles of silver. So we can always do this by completing a mole ratio, which is a very useful strategy. So I'm running a little bit out of space. Let me erase some of this. I'm going to write it down over here on the side. So what I'm going to say is the moles of silver, take the moles of what I know, which is the silver sulfide, now you're going to multiply this by a ratio, and how I do my mole ratio is I put the units that I don't want on the denominator, so that's what I want to cancel out. I don't want moles of Ag2S. I do want moles of Ag, so I'm going to put that on the top. So moles of silver sulfide will cancel out. Now what numbers do I actually put in my ratio? Well, look at my chemical formula. I know that for every 1 mole of Ag2S, there are 2 moles of silver. Okay, so it's a 2-to-1 ratio. So therefore, the moles of silver that I removed was rounded to this 4 sigdigs in this question, right? Or 5. Okay, the answer key is showing 4, so we'll do that. So the moles is 0.08289 moles of silver. That's what was removed off of the tarnish. Okay, and that's how we do a question like that with a mole ratio. Let's move on. So rhodium plating is a process used to protect sterling silver from tarnishing. Okay, so this is a good electrochemistry application. This involves electroplating or depositing solid rhodium onto the surface of the metal from an acidified solution. Oxygen gas is also produced during this process. So a table of half reactions is shown here, and in question 1, it says to write down the balanced Net-Ionic equation for the plating of RH from the acidified solution. So all I have to really do is use my data, and when you're doing your Net-Ionic balanced equation, you have to be careful of one thing here. So this is correct. The way this is, the first equation is written, this is going to be my reduction, and this will be my cathode. So I'm going to say this is my red cat, because for the plating, you want this element to be the product. So you're plating this rhodium solid, that has to be a product in this equation. What we need to do for the second equation, because both of them are shown as reductions. So for example, like it says oxygen plus hydrogen plus electrons. So we want this to be the oxidation. And also we know that because it says oxygen gas is produced. So that oxygen has to be a product. So I need to flip the equation. And this is my oxidation. And this will be the anode. We say it's anox. So the equation will look like this. And I also need to do one thing. I need to make sure these electrons are balanced. So we'll take care of that after. So let me flip this equation first. So I'll get here 2H2O produces O2, 4H plus, that's the acidified part. Remember, like balancing in acidic solutions, and 4 electrons. So I need to balance this before I add them up. So I need to make, so there's 3 electrons gained here, 4 electrons lost. So it needs to be 12 and 12. So I'm going to multiply the reduction by 4 and the oxidation by 3, and I will write it down because this will help me. So for the reduction, I'll just do it up here. This becomes 4RH 3 plus 12 electrons produces 4RH solid. And then for my oxidation, I'll multiply it out over here. It will be, so I'm multiplying this one by 3. So 6H2O produces 3O2. Sorry, this is a little messy. Plus 12H plus. Why did that, sorry, let me make a little correction here. Why did that pop up? So this was, sorry, going back here, 4RH 3 plus. Okay, going back to my oxidation. Where am I? Plus 12 electrons. Is that it? Okay, so when we add these up, these 12 electrons will cancel out, and then we'll add up the rest. So we just copy this carefully here. My balanced final equation is 4RH plus 6H2O produces 3 oxygen, 12H plus ions, and 4RH solid. Okay, I think that is, yep, that's the right answer. So remember to review redox and oxidation reduction, cathodes, anodes. Let's do one more question here. Calculate the value of Ecell for the reaction in part D1. Okay, so for this equation here. So there's a couple different formulas for the Ecell. I like to use this version where Ecell equals E cathode plus E anode, flip the sign. So what I mean, okay, so let me just explain why I use this and what I mean by that. If you look at the data table, so let me just quickly change this for a second. If you look at the data table up here, these E values are written for, these are both shown as reductions. So they're both shown as essentially as cathodes, right? So when you look at the anode, we have to flip the sign because we actually flip the equation down here to make it an oxidation. So hopefully that makes sense. That's important because it'll change the sign of our answer. So in my answer for Ecell for this one, I will get the cathode is positive 0.80 volts. The anode becomes negative 1.23 volts. And so the Ecell will be negative 0.43 volts. All right, and hopefully that makes sense. We'll do one more before we go to the next video because this question's related. Based on your answer to D2, explain why this process requires the use of an external power source. So remember that when you calculate Ecell, if you get a positive Ecell, that's we call that a galvanic cell. So that's spontaneous. That's a spontaneous redox reaction. Positive Ecell values will, whatever gets oxidized, that will normally get oxidized, and whatever gets reduced, that will normally get reduced. But when you're making an electrolytic cell or doing electroplating, you will get negative Ecell values, and that negative sign indicates I need 0.43 volts to actually plate this rhodium metal onto my electrolytic cell. Okay, so the answer here is, why do we need an external power source? Basically because Ecell is negative. And so therefore it's non-spontaneous and energy is required. All right, so we'll continue the next part on the next video.